Good afternoon to all from the editorial board of BuildUp Portal. For the ones who are attending a BuildUp webinar for the first time, welcome. For our returning audience, thank you for renovating your interest. Just a brief explanation of what is BuildUp. BuildUp is an European collaborative platform in the field of energy efficiency in buildings. It is continuously updated and it represents one of the key sources of information on the topic of energy efficiency. You can register and become a member of the community, and you can also upload news, events, present case studies, results from projects, and so on. I would like to invite you all to navigate the portal. In the Learn section, you will find all the podcasts of the past webinars, so it's possible to listen to all the previous presentations. At the end of this webinar, the link to the video registration and the file to the PDF presentations will be made available in this section of the portal. It is a pleasure to host today's 9th webinar of the EPB Standards series entitled Example Calculation with a Set of EPB Standards, Whole Building Calculations from Components to Overall Primary Energy, which is organized in collaboration with the EPB Center and REVA, Federation of European Heating, Ventilation and Air Conditioning Associations. As you can see from the screen, we have scheduled a series of webinars on the topic of the EPB standards. Take a note about the next webinar, which is taking place on the 2nd of February at 12. I would like to invite you all to contribute and participate in this webinar. You can ask questions by typing in the box on the right side of the screen. They will be answered at the end, after the presentations. Now, I would like to present the agenda of today's webinar and introduce the panelists. First, Jaap Hogeling, Chairperson, SEEN TC371, Energy Performance of Buildings Project Group, will do a brief introduction. Then Dick van Dijk, EPB expert from the EPB Center, will focus on the building envelope, how to identify the starting point of a nearly zero energy building with heating and cooling needs and partial performance indicators. Last but not least, Laurent Sokal, independent EPB expert, will focus on technical systems, influence of design and operation mode on dedicated indicators and overall building performance. So now I would like to leave the floor to Jaap Hogeling. Please, we can start the session.
Thank you very much for this kind introduction, and welcome to our webinar in this new year. We welcome all those who are interested in this webinar on the calculations with the set of EPB standards. And today we will say a few words about the calculation on residential buildings. My background is that I'm chair of the SEEN TC371 on energy performance of buildings, and I was project leader of the mandated work of SEN to develop the set of EPB standards, and the participation of many SEN TCs and ISO TCs is also part of this work. I'm manager of international standards at ISO in the Netherlands and initiator of the EPB Center, which is an initiative from ISO and REVA. The goal of the example calculations is to demonstrate the functionality of the calculation as described in the standards, to demonstrate that the calculation works with practical cases and available features to describe the energy performance of buildings and their installations. The sensitivity of the calculation procedures to demonstrate which impact of single data or group of data on selected calculation results have, and the usability of the procedures described in the standards to demonstrate the data input, avoiding unnecessary input complexity, and description of practical system configurations, and showing useful results. This we did on individual calculation modules, and in this seminar we will show how it works on a whole building calculation procedure. and that is focused on the residential building case. It will demonstrate how the EPB standards enable to identify the impact of building and system design. Think of good or bad insulated buildings, system technology choice, renewable inclusion, and different outdoor climates, a cold and a hot climate we take as an example, and assumed use of user patterns and operational schedules of occupants, and to show their impact on the overall energy performance. We will also demonstrate how choices, national choices for partial and overall EPD numerical indicators can effectively control the energy performance and set the reliable minimum energy performance requirements. So to show that the EPB standards are great tools for the EPB calculation, if using hourly calculation method correctly, you can extract a lot of useful information to decide on the best building and system design by comparing different possible solutions. When finally properly built, installed, and correctly commissioned and used and operated, this is the best starting point for a well-performing, energy efficient, and possibly, and that is depending, of course, on the connected energy grid, a zero carbon building. Thank you for listening to this short introduction, and I first want to introduce the first speaker with content. Dick van Dijk will be there. Thank you.
Good day to all of you. So thank you, Jaap, for your introduction. And my presentation will be, so my name is Dick van Dijk. My presentation will be on the building envelope and the energy needs for heating and cooling, and the link to nearly zero energy buildings and partial performance indicators. You can find here a little bit about my background. I will skip this slide because you can read it later on when you look up the recording of this webinar. So starting point is the energy needs. And the EPB standard on the energy needs is the ISO 52016 part 1, heating and cooling needs and indoor temperatures. And in Europe, it's the same standard is called the EN ISO 52016 part 1. ISO, EN, ISO are the same standards. So if you presented or listened to the recordings of the previous webinars, you may wonder, well, this was already presented at previous webinars. That's correct, but the focus today is on the illustration of the impact of some national technical choices with regard to, for instance, the standard conditions of use or simplifications in the methods, and to illustrate the impact of some design choices and how to value the result in terms of energy and comfort. And then this brings us to the partial performance indicators. Yeah, these are actually national policy choices, and we have a EPB standard EN ISO 52018 part 1 for this, which we call a post-processing standard because it gives you the indicators. And in this case, the indicators dealing with the building fabric and the energy needs for heating and cooling. And more in general, I hope to show in this presentation that EN ISO 52016 part 1 is fit for the purpose, and also the spreadsheet that we use for showing this fits the purpose. So let me continue with a very important element of the set of EPB standards, and you may be quite aware of this if you attended one or more of the previous webinars. That is that each EPB standard contains a limited number of possible choices that you can make at the national level. And this is done in a way that each standard has an Annex A, which is an empty framework, which contains a template for specific choices in the method or specific input data or references to other standards. This is mandatory to use. So this can be used for the national choices. And then there is an Annex B, which is just informative, which has filled in this framework with default choices, input data references, is optional for use and also can serve as an example. And I'll come back to these national choices in the discussion on the example cases. And yeah, so as I showed here, webinar 1, if you go to the recording of webinar 1, you find more details of that. Other background information can be found also in other webinars that we had last year. So a complete overview of the EPB standards, webinar 2, webinar 4, the hourly versus the monthly method, which partly comes back in this webinar. Then webinar 7, introduction to the example calculations. I'll repeat a little bit of that for those of you who were not able to attend the previous webinars. And the last webinar before this one, coupling of thermal zones and heat pump system calculations. This subject also comes back in this webinar in a more detailed way. So we'll see that later. And the overview of the whole series can be found in this link, but that was already explained in the introduction. So another feature of the set of EPB standards is that it follows a modular approach. And there are several ways to illustrate this. So this is one of the ways where you have information on the building fabric, heat gains, climatic conditions, indoor environment requirements. That brings you to the energy needs for heating and cooling and indoor temperatures. So that's the main subject of my presentation, EN-ISO 5216. And the calculated energy needs are then an input for the standards on the systems, heating and cooling systems, ventilation. And there's also an interaction with ventilation, by the way. Well, and as soon as you have the information for all the systems, you get the conversion to primary energy, and that is the subject of the next presentation from Laurent Sokal, who will deal with the whole building simulation, and then you end up with primary energy. But this was also a specific subject of previous webinars. And then finally, you have this post-processing, and that's shown also on this next slide, on this slide. So the EN-ISO 5218 gives you the partial performance indicators as a processing, and those deal with the building fabric and the energy needs. So the tools that we use for the example calculations are in most cases the spreadsheets that are available for individual standards for each module, so to say. So why use these spreadsheets, or why have spreadsheets? This is also a slide from our previous webinar. Well, the spreadsheets which are publicly available or in preparation. You can check the website of the EPB Center for that. They are mainly intended to demonstrate and to validate each EPB standard. Having said that, yeah, there is a disclaimer that the spreadsheet is not always exactly the corresponding standard, because spreadsheets have some limitations in general, and also in this case, the spreadsheets have some practical limitations on the input data that that you can use in the spreadsheets, and also some special features may not be included. For instance, an quite important one, is multi-zone calculation is not covered at the moment in a spreadsheet. If it comes to energy needs for heating and cooling, you can have attached unconditioned spaces or sun spaces. They are not covered at the moment in the spreadsheet. So that's the disclaimer on the spreadsheet. And the main goal for the spreadsheet is to demonstrate and validate each standard, as I said. So this also means that the highest priority for in developing these spreadsheets was that they are technically correct and transparent. Where possible, all the intermediate results are shown. And at each step of the calculation, references are given to the corresponding clause or the formula in the standard. So this means you can use these spreadsheets to check the standard, and also to, as Jaap mentioned in the introduction, to test the usability and the sensitivity of the standards. So this means that the lower priority got the user friendliness and the performance of the spreadsheet, so the speed of the calculation. So they are not intended for daily practice to assess the energy performance of the building. Okay, so that was the introductory part, and now we come to the example cases. So for the examples to be presented today, both myself and Laurent Sokol used the residential building as shown here, which is the same building as described in the technical report which accompanies the 5216 part 1 standard. So this technical report, and we made some variations on that example. So the variations are for today are that we chose 2 different climates. We have chosen the hourly calculation method. Jaap already mentioned that the hourly calculation method gives you a richness of the results which you can benefit from. The 2 insulation levels, continuous and intermittent heating. Also, I'll show something on the assumed operation of movable solar shading and the impact, and also the impact of other maybe minor simplifications. What happens if a cooling or heating system is absent in this dwelling, and the difference between heat pump and boiler. And this is the last one is the main subject of Laurent Sokol's presentation. And then I used 2 colors here. So the green colors are mainly choices you make at a national level. So choices which have to do with the calculation method of the conditions. Of course, the climate is chosen at the national or regional level. Also, whether you are allowed to use an hourly calculation method or a monthly calculation method. Of course, insulation and non-insulation is a design of the building. Then continuous and intermittent heating. Yeah, you might argue about this, but I would say that it's the choice of the calculation method, whether you assume a standard occupant behavior, whether you use continuous or intermittent heating, which might be a function of the type of heating system or whatever. Then also the operation of movable solar shading. Yeah, you need to assume a certain operation of that certain user behavior for that, and to have a transparency, uniformity, reproducibility of the calculations, and a level playing field, you assume some user behavior for that. So that's also, in that case, a national choice. And for the absence of systems, I'll come back to that later, but that's, yeah, you would say, well, that's a design choice, whether or not you have in a heating dominated climate cooling system installed in your building or not. But I'll show you that this also has an effect on the national choices. Okay. Yeah, just to remind you, also a picture from one of the previous webinars. So the EN ISO 5216 part 1 for the calculation of the heating and cooling needs and indoor temperatures. It contains both an hourly calculation method and a monthly calculation method. And they use the same input data and boundary conditions. So that makes it easy also to judge whether or not a monthly calculation method would fit the purpose. And also the spreadsheet, which is available on the standard, calculates both the results with the hourly method and the monthly method. And if you want to know more about this, there is one of the previous webinars was specifically dealing with the difference between the hourly and hourly and monthly calculation method. So the hourly climatic data were also mentioned in the previous webinar, and so we said there you can use test reference years for a given region of country. If not available, you can use the recently developed typical meteorological year generator developed by the Joint Research Center of the European Commission, which gives you the hourly weather data for almost any location and period of choice. And what is new is that we developed a tool at the EPB Center to convert the generated data for the typical meteorological year to make it suitable as an input for the set of EPB standards. And that's actually an input for this standard EN ISO 52010 part 1, which converts solar radiation data from horizontal plane, which normally the measured data, to vertical and inclined planes, for instance, for PV panels, solar panels, or for windows, etc. So this tool is now available, and here you'll find the link for that. So now coming to the actual cases. So let me first show a few base cases. So if you compare for Athens uninsulated to insulated dwelling, then of course, as expected, you see that the heating needs decrease strongly from uninsulated to insulated. Cooling needs increase, but not so dramatically in this case. And then you see a difference between continuous heating and intermittent heating, so meaning using a nighttime temperature setback. And here you see for the uninsulated case, the difference or what you gain in energy with intermittent heating is 9%, and for an insulated case, 6%. So the observations are, well, for the national technical choice of the method, you can assume continuous or intermittent heating. And you see here the effects. This could be, and also depending on the national tradition, you could say, okay, we go for continuous heating. We assume continuous heating because the difference is not so big, and this is more conservative, and maybe also in line with the national tradition. You see also that Athens, in this example, went from a heating dominated to cooling dominated case. And you see that the heating nowadays for the insulated building is small, the amount of heating, but then the question is, well, if you ignore the heating, if there's no heating system, would this affect the comfort significantly or not? And that will be shown in one of the next slides later on. And before I forget, a little disclaimer on the calculation results. All these results shown today by myself and also by Laurent Secal are subject to review. They are part of a number of case studies that we are performing at the moment. So they are work in progress, so to say. The final results will be published at the EPB Center website later this year. Going to the next base case, going to the other climate, Oslo, and of course, as you expect, this is heating dominated, so uninsulated case and insulated case. But you see for the insulated case that cooling becomes not negligible anymore. And again, you see the intermittency is having just a small effect, especially in new buildings. So again, for this cooling, if you assume that there's no cooling in the building, what happens to the thermal comfort? Then one of the special calculations. So for these calculations, we had to assume that solar shading devices are used in a certain way. So movable solar shading devices, so say internal Venetian blind or something. And in this residential building has a large south window, so this has quite an impact. And initially we just set as a threshold value for moving these blinds down 200 watt per square meter of solar irradiance on the facade. And so that gave us the heating and cooling demand. But if we change this assumption to 400 watt per square meter, then you see that the heating drops significantly, very significantly actually, but on the other hand, it's just a small number. This was for Athens. But also the cooling, you see that this was a big number and now increased very significantly. Just simply due to the assumption of how the occupants will use the solar shading device. So this has a strong impact on the results. So one of the choices in the National Annex 2, in the Annex A of the standard is about the level of solar radiation where you start to use the solar shading device, or you could also choose nationally a more complex operation schedule. And so the question is, which assumed standard user behavior is realistic, is the most realistic? And yeah, that's one of the national choices you can make. Then another one which might not be so obvious at first instance. So if we look at the insulated building in Athens, how sensitive is it for the color of the external opaque surfaces? So in many cases you would say, well, I don't want to check for my building what are the colors for the roof and the opaque facades. So let me assume just an absorption factor for solar radiation of 0.8 as a default, and saying everyone should use this value. And then you get this value as we've seen, these values as we've seen before. But then if you say, okay, but let's say if it's highly reflective, an absorption factor of 0.2, so clear white, then you see that the heating needs increase drastically, but still it's a small number. But the cooling needs also decrease significantly. So as an observation, you could say the color, the solar absorbance of the external surface has an impact on the result. So then it's again a national technical choice whether or not to take a default value or an actual value, and a default value could be a high value or a low value or a medium value. So these choices are there, but they have a strong impact on the results, as you see. Then I come to what I mentioned before. So what happens if you assume for Athens, for instance, that there's no heating system present? So with the heating system present, we had about 10% of heating compared to the cooling demand. And so you gain in your energy 9% if you have no heating system. So this will be beneficial for the energy performance of your building. You have no heating system, so you don't use heat energy for this heating system, and you gain 9% at least on the energy needs. Well, but is this fair? Because on the other hand, if you look at the mean indoor temperature in February, it drops now to 17.6 degrees. And this is what you only can see correctly with a hourly calculation method. So there's a national choice, and in this case I would say it's a policy choice for a level playing field if there's no system present. Well, do you assume then a default system, the fictitious system? So you say it's mandatory to have a system in your calculation, then not a real system, but a fictitious system. So that the gain you get, the beneficial effect of having no heating system, is compensated. So then you have a level playing field. Or another option is, well, if you say, well, yeah, but this is not so big, the 9%, I like to see, and the system is still absent in reality, and the comfort is still bad. I prefer, as a national or regional authority, to show the impact of the absence of the system on the thermal comfort. So then you could introduce a thermal comfort indicator. And in this case, this could be the mean indoor temperature in the coldest months, in this case, February. Another option would be, so that's the average temperature in February. Then another possibility could be to show the temperature weighted hours with the indoor temperature below 20 degrees or 18 degrees or whatever you want to choose. Which you see here for the months January, February, it's quite big. And so this could be a national choice to have this as an indicator. And then you could have a national requirement that allows a maximum value for this, and to take certain measures if you exceed a maximum value. Actually, you could convert this number of temperature weighted hours into the average temperature for the whole month, which I've shown on the previous slide. And there are more combinations possible, but for the sake of time, I'll skip these. So the similar for Oslo, what happens if there is no cooling system present? Again, that saves you by coincidence, again, 9% in energy. So wow, I have a very good building because I save 9% energy because I have no cooling system. But here you see that the mean indoor temperature in the warmest months now rose from 25.9 degrees to 28.9 degrees. So again, you could have as a national choice to say it's mandatory to have a fictitious cooling system in this case in your calculation, or you could add a separate thermal comfort indicator. In this case, could for instance be the indicator could be that you are in the warmest months 2.9 degrees on the average above a certain threshold, in this case 26 degrees. Or again, similar as for the previous case, in essence, without heating, you have now a number of hours with overheating, temperature exceeding 26 degrees. So temperature weighted number of hours, or accumulated temperature difference, you could also say. And you could say, okay, at national level, I want to put a limit to these values. And yeah, then I come to the last element of my presentation, which is about heat pump systems. And this is just a short introduction because Laurent Sokal will tell much more about this. But this is focusing on what we did for on the energy needs part. So the energy needs for heating and cooling are coupled to a heat pump system in the calculations. And why is that? That's because the thermal capacity of the heat pump depends on the variable conditions. So there's the conditions vary hourly, so and it has an impact. So the conditions for the calculation of the energy needs have an impact on the maximum capacity of the heat pump. And if the capacity is not enough to cover the needs, you get an undersized system in a bit in the same way as we shown in the case of the absence of the systems. You can show the discomfort. And also the thermal losses of the system are variable, so they change each hour. And if these losses are dissipated in the thermal zone of the building, they contribute to the internal heat gains, so they will decrease the heating needs and increase the cooling needs of the building. So these are the reasons for making the coupling. At the previous webinar, we also showed the coupling between energy needs for the building and the heat pump system, and there we used a fully detailed coupling for each hourly time steps. We had a complete interaction between the two calculations, which was quite complicated. Now we do it for these cases simpler. The reason is to simplify it is that the detailed interaction, as shown in the previous webinar, is quite complicated, and it mainly aims to show the sensitivity for the variable hourly properties and the conditions. So now we have seen that we can simplify it. We have now calculation of the heat pump, from which we get the available output for heating for all hourly values for the full year. That's an input for the heating and cooling needs and indoor temperature calculation according to 5216 part 1. And then the output goes, again, the hourly values for the full year go into the heat pump calculation again to calculate the COP, the performance of the heat pump, which depends on the conditions and on the energy needs. And this is all presented in Laurent Socal's presentation. And I'll just show one case because that relates to what I previously mentioned. So if you have a small heat pump, for instance, in Oslo, an insulated residential building, and you want to know if this size of the heat pump is enough to cover the needs. So we assume a continuous heating and not intermittent heating for this case, because the heat pump is quite small. And so you see that heating is covered almost completely. And also the mean indoor temperature in February is not much below the desired 20 degrees in this case. And then similar as before, you could present this as an indicator, as a temperature weighted time below a certain base temperature, in this case 20 degrees. And probably this will be below, if you set a national limit to this indicator, then it will probably be below the threshold level, and then it's acceptable. But this is thanks to the assumed continuous heating. If you choose intermittent heating, then it would not be a sufficient size for the heat pump for this case, but that's not in this presentation. So the conclusion is that the EN ISO 5216 part 1, which is one of the core EPB standards for calculating the overall energy performance of the building, is able to show the impact of assumptions in the boundary conditions of the calculations and in the conditions of use, and also to show the effect of simplifications in the calculations. And also it shows the impact of some design choices, and more specifically how to value the results in terms of energy and comfort using partial performance indicators, so the energy needs and thermal comfort indicators. And hopefully I contributed with this presentation in showing that the standard and also the spreadsheet that we used for these presentations is fit for the purpose in terms of the functionality, sensitivity, and usability. So that concludes my presentation, and I would like to give the floor to Laurent Socal, who will continue with his presentation.
So, thank you, Dick, and good day to everybody who is listening to us. So I will continue and proceed with the part about the installation in the whole building. As before, my background, I will be summarized. I don't know yet my job when I will be older, so just skip because I don't know really what I'm doing. Well, the building, you know, it has been already been described, is the building that is used in the 52016 as an example. So you've already been told we have the alternative Oslo-Assen, insulated, non-insulated, 150 square meter floor area. I will compare as well floor heating radiators, a boiler heat pump. We will consider a domestic hot water store of 160 liters. No PV or thermal solar in this example. I will just tell you where you can couple them eventually, possibly, and natural ventilation with 0.3 or 0.4 air exchange rate, which are reasonable for an average residential building. And heating needs already been explained before. And what is interesting is the connection with the heating need calculation, taking into account the limitation that you might have in your heating system. So the climate as well has been already described. So we choose two extremes, and it is here you see the bins for Oslo in the blue, and for Essen in red, and they have been generated using the spreadsheet combining EN is ISO 52010, and the data from the meteorological years that are issued by the JRC Center. And system calculation. So what's the challenge for the system calculation for a building? So first, you have to take into account the interaction between the system and the building envelope. So typically, it might be for heat pumps a limited power available for heating, and this concern recovery after intermittency, or when you have to reload the domestic hot water storage, and it takes maybe 1 hour to reload your store, and losses of the installation. And be aware, it's not only a question about the power available by the generator, it depends also on the size of your heat emitters. For example, for a boiler, the limitation comes from the heat emitters. So you might have multiple limitations. And the challenge is to avoid iterative calculation, because this would use a lot of time, and take into account the operating condition, because we have devices which are very, very sensitive to operating conditions. The heat pump is one of them. And the solution to these challenges is an optimized calculation order. So you have to set up your calculations right order. We'll see this. And your modules shall take into account the operating condition in a proper way. And more details on specific items now, I will have to go a little bit fast because we have not so much time, and there are a lot of examples. But you can find more detail on specific calculation procedure on the N standard in webinar 6 if you want to have more details. So when I mean the good order of calculation, typically we have the heating needs, and if you want to avoid iteration, you should start with all the calculation of the system which are not influenced by the building condition. I mean, for example, domestic hot water. It doesn't matter the temperature in your building. You can calculate this straight before your building needs. So if you go through your domestic hot water needs, you can calculate the distribution for domestic hot water so that you know how much heat is released in the building by the domestic hot water network in advance. And then you can calculate your storage, and here too you will have some heat release to the ambient if your store is inside. And you might also calculate your generation system just for domestic hot water, not yet for heating, because you don't know yet the heating needs. So you can pass the information to the building needs calculation. Sorry, I only have some amount of heat available because, for example, I already had to satisfy the domestic hot water production, which is what happens in reality when you have a priority for domestic hot water. Of course, if they are separated, this doesn't apply, but very often use the same generator for both heating and domestic hot water. And giving this, you can calculate the needs, now knowing what's available. And in this case, then you proceed when you know the needs. Then you proceed with the heat pump, or in alternative with the boiler, which could be a backup, for example, and then cooling system, and then you get your overall energy performance. Of course, you will have still some interaction bags. I mean, some losses from systems that will occur in the same hour. So you might decide either to iterate or to push them to the next hour to avoid to spend too much time for the calculation. This is another possible choice, and it has to be done nationally. But if you have a clever calculation order, you may solve most of the problems in advance. So let's start our calculation. So I actually used all the spreadsheets, or most of the spreadsheets for all the calculations based on is done with spreadsheets for the EN series. So for example, domestic hot water needs, you start from the calculated daily needs, and here, for example, a detail, what's important is an amount, a volume of water at the draw off temperature, typically 42 degrees, which is also a national choice. And here you can see an example of the influence of climate, because you need the water at 42, but the water, typically the cold water, comes from the piping in the ground, so it is at the average yearly temperature. So in essence, you will have 17.8 degrees of your cold water and 6 degrees in Oslo. So you have a difference. Even if you always you still need something more than 200 liters per day at 42 degrees, depending on the cold water temperature, your original need is different in Essen and Oslo. So, and it's interesting, not only the kilowatt hour per year, but also the kilowatt hour per day. So you see that you have a generator which is 4 kilowatt power. In the worst case condition, it takes 1.5 hour or 2 hours to fulfill domestic hot water in one day, approximately. Here we are ignoring some of the losses. And you have also here the impact in kilowatt hour per square meter per year of the domestic hot water needs. So it's something relevant when you can kill heating. Domestic hot water is still there, and this is the average power. This is another way to compare the two situations. Then you always start in this schematics by the daily needs at free draw, at the temperature of draw-off temperature, and then we'll use this during the day and distribute along the day with a profile. I use the Excel profile. This is typical. The next step is storage, and in this case, in webinar 6, I think we dealt with the storage with the 4-layer complete model for thermal solar. In this case, we will use only 2 layers and to simulate just a storage when you have no thermal solar. This is possible. This is just a bunch of data. It's just geometry, and here this heat loss coefficient, you can get it from the label of your storage, so no real problem. The fact is that you use these 2 layers. That enables you to do a calculation and to see the temperature in the 2 layers. And this is a sample result from a spreadsheet that I use for this calculation. And you'll see always the temperature at the end of the hour. And in this case, I had the set temperature 50 degrees and reload at 45. And a possible application here, the sentence is cut. But if you go in a sub-hour details, you can use this to see if your sizing of your store is correct. And in fact, this is a detail about a typical day, when a typical hour, sorry, when you have the storage reload. So this is the beginning situation. Your store is still a little bit cold because it's waited for, so there has been a bunch of hours without any draw off. So now you have a draw off, you cool down the bottom part, and there's no heating draw off, so there's no heat taken for heating in this case, so go on. No solar heating, go on. Then you turn on your backup heater because you are below 45. So you heat up so that you get to 50, and then you take into account the heat losses. And you can see what happens during 1 hour. And this is repeated for each hour. And we use only this part of the model. And this is working fine. Now we come to the heat pump. And we already come to the heat pump because we have to calculate what happens with domestic hot water. And of course, the heat pump is an interesting machine, a very efficient machine, but its performance is strongly dependent on operating conditions. And what you see here is a performance map which is used inside the EN 153.116-4-2, so the EN standard for heat pumps. And you fully describe the COP performance map and the full load capacity. And that's very important, full load capacity, because this is what will enable us to decide, can we fulfill our task of heating that building and producing the domestic hot water. And you see, it depends mostly on outdoor temperatures. This is an air to water heat pump, but there is also some dependency on the flow temperature. And we will use this in the next slides. And it's important that it's not only a question of temperatures, it's also a question of part load. This is a result of a stress test on this standard. What is a stress test? You assume that you apply an increasing load in kilowatts during your hour, and this will result in, first, you are contributing with your heat pump until you reach the maximum output power. So we'll then use the backup, and if the backup even is not enough, then you will have to ask heat to another generator. And you see that the COP, of course, is you have the full load COP. Here we are at full load, but if the load is reduced, first you have a slight advantage, but at part load, the COP will decrease dramatically. So if you have a severe part load, you will have a decreasing efficiency, and you have to take into account this, because heat pumps will very often work in part load condition. And here the COP is decreasing because, of course, for the heat pump it's constant, but you are using the backup, which is electricity, so it decreases, and that's fine. And you repeat this calculation for a different air temperature, and you see that even the available heat output is changing. At 10 degrees, you have this 15 kilowatts, and at -4, you only have 11. All this is taken into account in our calculations. So domestic hot water with a heat pump. This is the first thing we will do, because we need to know how much time is used for the heat pump, which is doing both heating and domestic hot water. We are running just the first part, and just set the heating to 0 to know this. And these are the assumptions I already told you. And the result, of course, is in Athens, as you might expect. You use less electricity and you have a higher COP because, of course, it's an air to water, so 3.2. This is an average of the whole year. And Oslo, of course, you need the double, not only because the COP is lower, but because you need more energy, because the domestic cold water is colder, of course. And in Oslo, you need a couple of hours a day. This will have some effects. And here you could start some discussion, because this was just a yearly value. And if you plot, for example, the monthly value, you start seeing that, okay, there will be a threshold where efficiency of the heat pump is lower than the boiler. That depends on your conversion factors. This is part of the 52,000-1, and you might, in any case, find thresholds. You make a ratio between your conversion factors for electricity and fuel, and you have a threshold. Here it's more advantageous to go on the heat pump, and here it's more advantageous to go with a boiler, because of the low performance and the fact that electricity, if you use the European conversion factor 2.5, below 2.5 of COP, it's better to use for an efficiency point of view. Non-renewable primary energy, it's preferable to use the boiler. Nevertheless, we can discuss. You might do a lot of consideration, and here you can see the result of. Here it's a result of the calculation of the available power, and you see that the available power for heating is varying along the day because of external temperature, which is the most important factor in the available power. And at some time, the available power goes to 0 because we are reloading the domestic hot water store. And here we have 2 small reloads, and you see this pattern, and this will be the input for the energy need calculation 52016. This is the big line is what is available for heating at that hour. And of course, here you will have a temperature drop inside your building. This is not available. And here you have the data for the worst. So what will happen to the building temperature? Is there any significant discomfort? And that will be what he's calculating next. So calculating needs, this is done, this is the next steps. So now we have the information of the available capacity for heating. So this will be done by 52016 as Dick van Dijk explained you. So first pass is calculate available power for heating, what I've told you, and be aware that this is dependent on the control strategy, for example. In this case, I used a heating curve. So, and this is quite a common option. So depending on the external temperature, I know the flow temperature, and the limiting factors could be the generator, heat pump typically, and the sizing of emitters. And if you know the flow temperature, you know the sizing of your emitters, you know the maximum power that can be emitted inside your building. This has been all taken into account, as you will see. And the second pass, you calculate the heating system. First pass and second pass, of course, across systems, if you remember the slide with serpentine. So following this, I did a number of heating system calculation. Not all the possibilities or the combination of insulated, low or non-insulated, Oslo, Athens, heat pumps, boiler, but only some relevant combinations that we will see and comment. So just start with Oslo, low insulation, condensing boiler and radiators. So low insulation, actually 0.8 and 0.5 as a U value in some countries should sound already rather good, but of course in this climate is not that much. So here you have an information about the heat load of this building, 13.5 kilowatts. We are at the limit of the floor heating. These are the amount of the heating needs. Of course, the cooling is nearly nothing, and typical application with radiators. And I like always to present this in the shape of a design energy signature, so that you can have an idea about the required sizing immediately. And what happens if you have continuous operation? Nothing strange. You just have your constant indoor temperature. You have plenty of power and no problem. It's working fine. Now you can also take into account your return temperature, and we are running on radiators. So if you take into account the fact that you have a heating curve, that you have thermostatic valves typically, so you will have this kind of behavior. Here you have the boiler power output during the hour, and here you have the return flow and return temperature. And of course, the power of the condition, the flow temperature with the same required power output can be different. So in that case, to adapt, you have a different type of delta C on your installation. And you can see that most of the time you're below 40 degrees and sometimes even below 30. So you might use the condensation in your boiler. Keep this in mind because we'll see something. And now we are trying to compare the intermittent operation. Dick van Dijk told you correctly that you have no significant savings or not really important savings compared to the problems you might have in comfort. Here you can see, for example, with the same conditions, we are operating the system only 17 hours per day. We have 7 hours setback during the night. And first thing, not so much saving, but you need a higher sizing. In this example, I shifted from 16 kilowatt to 20 kilowatts nominal size of emitters. And here you can see, for example, what happens to your system if you only take into account the available hours. You are increasing the sizing of the system. So what's a side effect on the intermittent operation is that you have to oversize your system, and that's cost, that's energy embedded in your systems. So you need to size a system which is 40% more powerful. For a boiler in a small house, that's not an issue. For big buildings, that's different. And here you see, for example, what happens to the temperature. And with these assumptions, and you see that we took into account the fact that we have a limited available power. And these oscillations in the peak means that I'm taking into account the heating curve, which gives a maximum to the power emitted, which is not the power of the boiler, but the power of the emission system at the given temperature. And here you see what happens. And you might notice here that we are losing up to 6 degrees during the night, which is not really such a comfort. And here you see also the consequence. Despite we had increased radiators, here you have all the data. What happens is that you have to run at a higher temperature. And during recovery, you're running at higher temperature and higher power. That means that your boiler is less efficient. So your efficiency is dropping down. And I can say that probably it's a little bit underestimated, the drop in efficiency of the condensing boiler because of intermittency. And you can see clearly that here we are definitely 10 degrees higher in return temperature. So that means something for your condensing boiler, apart from being oversized and apart from being having a discomfort. And you see, as a final result, the difference between continuous and intermittent is even less than for the needs. And now let's shift to a heat pump. And we are now we are still in Oslo, and we now have a very well insulated building. Well, very well in some counties. Maybe for that countries 0.22 is not really very well, but nevertheless it's a good level of insulation. And here are the data of the result for the calculation, and you see that we have seasonal results. We have the required output to the heat pump for heating. You have here the required output for the domestic hot water. The cooling is nearly nothing. And here you have your seasonal COP. And here is the usual graph, and sees that more or less you need 4 kilowatts at -15. And of course here gains. And the question could be, here you have the curves of the full load capacity for 4 sizes of the heat pump I had available. And the question could be which to choose. And if we just think about heat load, and I just plot the heat load on this graph, and it looks like you need the size 8 as a heat pump to fulfill. And here we are at risk, because if you have low temperature, it's okay. If you have at high temperature, even with high temperature, you would not match it. So you should need even the size 11. Well, I use a size 4 and just have a look at what happens. And of course, as we can expect with the smallest heat pump, of course, with continuous operation in that case, you will see that of course you have some discomfort, but most of the discomfort is just linked to the reload of the domestic hot water storage, not really on the fact that the heat pump doesn't match the load for heating. Actually, it's nearly matched. And if you go into details, for the worst case, this is the worst day which you could find, so the coldest day, and you see that really here the heat pump was not matching the load, and you lose 1 degree for 1 hour, and that's when you have the reload of the storage. Here is the available heat is 0 because we are loading the store, and here you have some difficulty in recover, but here you are again at 20 degrees. So that's what happens if you dare to use your the smallest heat pump. It's important for heat pumps to be able to size them correctly, because here you can see already one effect. Here, this is the COP of the heat pump for all the hours in the heating season, and you see definitely the influence of external temperature. But what happens is that when you are in the warmer months and you should expect a higher COP, then the part load factor applies. So you have this drop in May and September of the COP because you are working at part load. That's why you have this cloud of dots here, while here it's when you are recovering after a stop, or when you have a higher need, or after storage reload. So all these effects are important to identify also in the correct evaluation of a COP. And this you need a Howley method to go through all these details. And here you see, for example, February is the worst month, and you see also here this curve is a COP monthly, and this is a load ratio monthly of your heat pump. And here really you have at very low loads. At below 0.25 you start losing efficiency. And now we can shift to, and that's important having this in mind, because that's important for consideration about sizing of the heat pump. You do not have to oversize it because it's costly and because you are introducing then a bad part load when you are in the mid-season. And Athens, we now move to Athens, and here the boiler is not very interesting, so we will deal only with the smallest heat pump. I start with a badly insulated house. You have the data here, a typical U walls of 1.1. Probably the roof could be even worse when you have no insulation, but nevertheless, I use 1.1, could be adjusted. A heat load is 8.5 kilowatts, and these are your heating and cooling needs for the heating season. And a solution could be just use fan coils, because the most important concern in this case is cooling. So if you have fan coils, you might both do the heating and the cooling. And very often in these countries, you are more sizing your installation on the cooling rather than the heating. So let's use the fan coils, and average COP is not that high. Why? Because we are running at 45 degrees. And if we have a look, the smallest heat pump is not really enough. You see here in February, we have some days where the heat pump cannot match the load. The smallest peaks here repeatedly are the storage reload, but this curve is the fact that we are not matching the required load for heating. So we should shift to the heat pump, probably the Model 6, and to fulfill our heating. But nevertheless, it doesn't change the results about the COP. This is just a question of identifying a discomfort. Same type of graphs, and here do you see that here you have the main curve, and here you have some points where you have a really low load, and the same representation of the load factor of your heat pump, and here the result for your monthly COP. And again, is a half season. Well, actually, this is concerning, and this also is important when interpreting data. Sometimes you have a high percentage, but it applies on a small amount. And this we have to remember. It's not really such a disaster, because here we are speaking of a small amount of energy that will be produced with a low COP. So the most important thing is really the part here. But nevertheless, don't oversize your heat pump, because you will have a lower efficiency. So here for comparison, I did the same calculation for a floor heating, so same results. And here you can see in our graph that the cooling part is appearing, but that's not the question today. And what has to be mentioned is that the average COP is now 5.15. So by the fact that we are running on a floor heating, this has dramatically reduced the flow temperature, and that therefore we have a much higher performance. And here always the same graph, not so much influence on the resulting temperature. So we are still slightly undersized. But the important thing is that now the COP is it's much higher. Same kind of behavior, so nothing new. It's just the level of COP which is quite higher, because we have used a different emission system running at a different flow temperature. And here you can see really the difference is that when we are in with the floor heating, we are running on this curve about COP. When you are running with the fan coils, we are running here. And in the region of the highest interest, the difference between the two domains is quite a lot. So What are the concluding remarks? With the EN standards and the hourly method, you can estimate the energy need and the efficiency of a complex system, and taking into account the interaction between the building and the systems. And the hourly method also is very important to have to identify the correct sizing of a heat pump and of the required backup. And the sizing of the heat pump is quite important for an economic reason. It's not only a question of a cost of operation, it's also a cost of installation if you are looking for the best life cycle performance. And it's the hourly method that allows to take into account the heat gains and the interaction with the building envelope and the risk of discomfort. And that's quite important to have hourly method when you deal with very sensitive devices like heat pumps, which are quite sensitive to operating condition. And EN standards do take this fully into account. And another remark that we had is that the intermittent use has heavy implication on the sizing and the operating conditions. So it's not just a question of, well, I turn off during the night and I save 5% energy. The question is that you need a bigger system and you have a discomfort. So this also is another consequence that is quite important and much easier to deal with when you have an hourly calculation. It's quite important. Maybe for the residential sector, it's not that important. In the non-residential sector with a very seldom occupancy and for the tertiary sector, dealing correctly with recovery and intermittency is quite a question, quite a subject, and it's very important also to take into account the building automation systems. But be careful, it's a powerful tool, hourly calculation. It doesn't require a larger input data than monthly. It's just using the data in a more complete and efficient way, but be very careful because any calculation relies on the quality of the description of the data. So if the building and system don't conform to the specification, and if your system are not properly commissioned, we assume a heating curve. Was that properly then commissioned? And if the gains are not correctly estimated, then you will obtain other results than design. So you need experience to fine-tune and to use correctly this tool. But this is not a question of the tool. This is a question of the variability of the data, of the situation we have to face. And is the energy performance the whole story? Because we said a lot of things about energy performance, but we are actually dealing with energy performance at operating, during operation. And well, there are several ways to weigh delivered energy. And you know that the attention is shifting from non-renewable primary energy to CO2 emissions. And we are now focusing in these standards only on the operation phase, but a lot of resources are incorporated during the construction of an efficient building and systems. So that's an example. Is it worth to spend thousands of euros for a more efficient system when the whole yearly cost is some hundreds euros? I think about Athens, for example. What's the importance of the cost for heating and what's the importance of the cost for cooling? And then make your choice of which system you will use. So calculation standards are great tools to solve this problem and to optimize your solution. It's not just a question of compliance. It's also a question of doing the work and having useful information also for the design. So if the EN hourly calculation method are used correctly, you can extract a big amount of useful information. But then, of course, in the real world, be sure that building and system are correctly commissioned and used. And an example is a heating curve for the heat pump in that building. And do always some back check of operational results of your designs. And so use the measured energy performance tools of the EN standards to compare and to gain experience. And a good design with a reliable calculation method is just the beginning of the story of your building. Will then has to live an entire life, possibly in an efficient way. Okay, and that concludes my presentation. And thank you for listening. And I give back the floor to the organization. Thank you.
Thank you all for your presentations. So we'll start with a Q&A with the first question, which is for Jaap. Is there a software tool available to calculate the overall energy performance covering all EPB standards?
Well, I will be very happy to say yes, but sorry, I have to say no. We don't have a software tool currently available that covers the calculation procedures as described in our standards on hourly basis. In many countries, they use national procedures. They are based for, let's say, 80 to 100% perhaps on the EPB standards, but they usually use monthly procedures, and that's included in their national calculation tools that are generally also computer programs. I know from several countries in Europe where they are working on hourly calculation procedures that really follow the EPD standards. And so I hope that in the near future we can expect some on the market. And I know also that several countries have, apart from a tool, also certification schemes to have clarity about the quality and the quality assurance of the tool and the people who use the tool, because having a computer tool is nice, but also being able to use it in a proper way and also to understand which input data are needed, as Laurent Sokal said, in a proper way is as essential as well. Thank you.
Thank you. A question for Dick, referring to the base cases, for example, in Oslo. What's the difference between insulated and non-insulated cases?
Yeah, in this case, we use as insulated case typically U values around, I believe, 0.2 for walls and roof, and actually the values which are also given in the technical report which I mentioned, so the EN ISO 5216 part 2. And then for the uninsulated case, we modified the assumptions to have, say, a few centimeters of thermal insulation instead of the more thick pack of insulation. And also for the windows, we changed from high performance glazing in the insulated case to single glazing. And also for ventilation, we changed the assumption for in the insulated case for say about 0.3 air change per hour to 0.9 air change per hour, assuming that there's more air leakage in the uninsulated case. That's about it. But the details will become available later on in the reporting on these calculations.
Thanks. One more question. Is the temperature you are referring to the air temperature or operative temperature?
The operative temperature, because the operative temperature is the one which gives you the indication of thermal comfort, and it's also in the standard the driving force for checking the temperature settings. So, and that can be done because we have this hourly calculation method where we have a thermal network simulation where the air is a node in the network, and also the surfaces, the indoor facing surfaces of all the constructions and the windows are calculated. So this gives you the mean radiant temperature coming from all the walls and the window surfaces. Means weighted by the surface area, and the air temperature. And the operative temperature is the weighted mean between these two.
Thank you. One more question. EN 16798/1/2019 includes air velocity in the variables which determine comfort in summer, and it has a large influence on comfort. May this be included in your example calculation?
The air velocity is not included in the calculations results, because that is a function of more detailed design considerations. And perhaps Laurent or Jaap can add something to that.
Well, we assume that the air temperatures are inside the air temperatures mentioned in the indoor environmental quality standards, so that you are inside a normal comfort situation for winter and summer conditions. I don't think, perhaps Laurent, you did look at air temperatures with your Athens situation?
No, the air velocity is not taken into account, because this is, I agree with Dix, this is a specific consideration when designing your emission system. If you are using air, or more, but it's not usual in Europe, when you have transverse ventilation, but that's typical of tropical countries. So this is a question really of comfort, which is not linked directly to energy consideration if you are evaluating a comfort index.
Yes, and as I said, we assume that system designers in Europe keep the air velocities inside the boundary conditions as mentioned in EN 16798-1.
Exactly. Should we do this way? You might compensate by changing or adapting your temperature to compensate, but this is done before. It's a design decision.
Yes, correct.
Okay, so I go on with the another question from the audience. If there are no calculation tools, then what is the point of all this? Calculation must be easily performed and transparent. Making an energy certificate for a building cannot be work for months.
Well, of course, the sense of this is fine-tuning, testing, and of course, I would say that some countries are going on, and in the near future, it is foreseeable that you will have software to do this calculation. The question is, it needs some time to be fine-tuned, and all this work is demonstrating this is possible.
Yes, and we know from some countries, I don't want to make promises and mention names, that they are working on a tool that covers the set of standards on the hourly basis. And many countries didn't do that after we published the standards at that moment, because they had to revise their national procedures to meet the requirements of the EPBD, and that was difficult enough. So what they did is they sticked to their monthly procedures, which were in their eyes more simple to handle. But I hope in 1 or 2 years there will be something on the market. But it is of course wait and see.
And we should maybe add also that there's a natural evolution of calculation methods. And that's following the evolution of technical systems and how what you ask to buildings. Because if you just in the year 80s of the last centuries, you just asked for some heat somehow, and that was quite easy and straightforward. But now you are starting to insulate, and you see that now it's a question of the balance between heating, cooling, ventilation, and by insulating we are killing the heating needs, but we are raising cooling needs and adding a lot of need of controls to keep the situation under control inside the building. And so this is more and more a question of what happens hour by hour. So it's just, I think, natural evolution shifting with time to an hourly method.
Yes, an hourly method that is also needed if we really want to connect the building to the local grid and to optimize it in a proper way, that we can show the impact of the grid connections and the other issues that are connected to the production of energy nearby and on the local level. Thank you.
Thank you. So let's go on with another question. Does the calculation method also cover non-residential buildings? Does the standard include an example for non-residential building and different building types? Could the conclusions be different for non-residential buildings?
I think Dick could you answer, because next one will.
Okay, yes, Dick speaking here, Dick van Dijk, and yes, the EN-ISO 52016 Part 1 is not only for residential buildings but also for non-residential buildings, and there are also calculation examples available. In the standard itself, we have an example of a simplified case, which is so-called shoebox case based on previous many years research activities, and in the current series of example calculations, we have also office buildings in mind. So we have draft specifications of office buildings to include in this series of calculations. And the conclusions will in principle not be different, but as Laurent already said in his presentation, some decisions may have a bigger impact on office buildings, for instance, than on residential buildings, and vice versa.
Yes, because of course the standard the calculation method is the same. What changes is the value of each data. For example, in the offices gains, it's you have more people, and so you have more gains. Ventilation is even more important, and also as I anticipated probably a bit too fast in my presentation, the intermittency can save a lot of money when you are dealing with the tertiary system. So I mean, adapting, for example, ventilation to occupancy, all these kind of things. So the result will be that it will be probably hourly method will be much more useful really in connection with non-residential buildings. At least this is my opinion.
Thank you. So another question, will the standards provide guidance for collecting data for use in the calculation, for example, a complete list of input parameters?
You can see this in each module. It has its input parameters, which are, by the way, more or less the same we have for multi-method.
Yes, I could add that in each of the spreadsheets that are available also at the website, you can find a list of input parameters for the respective standards. The challenge, of course, is to see through all these input data, because you could say the Pareto principle applies here, which means that 20% of the data is needed in the conventional cases, and 80% of the data which are listed for a standard are used for very special cases. So that has to be taken into account, and that also makes it a little bit more or less trivial to just make a complete list of all the input data, because then you should actually try to make a distinction between what are data needed for conventional cases and what for special cases. And then what is a special case? For instance, if you take a ground floor, it could be a suspended floor, a ground floor flat on the ground. It could be above a heated cellar, and so there's all kinds of details where you, in some regions, you can say, okay, this is a special case and that is a conventional case, and in other regions it might be completely different. And the same goes for systems, I suppose.
Yes, the same goes for systems, and we always have a list, and you distinguish, for example, product data. So data for a product will come from a catalog typically. So even if it's a number of parameters is linked to the model, then you have data that are operating conditions, which are typically default when you are doing a standard calculation for compliance or for an energy performance certificate, and you will really use all the potentialities of the standard when you are going to use this also for a design or for an energy audit. But in most cases, most of the data are preset.
Well, thank you all. I would close the Q&A here. So thank you to our panelists and to the audience. I would like to remind again the next webinar, which will be the last one of the series, and will take place on the 2nd of February at 12, with the additional example calculations. So thank you again.
Thank you. Thank you all.
Thank you all.
Bye all.
Bye.
Bye-bye.